Hi, Pre-calc. So let's finish up this unit. All right, so this unit, we have already done these pages. These were the first couple of parts of your unit. There's one more page, which I'll show you in a sec. But here are the answers, basically. So if you need to, please pause the video and go back and correct your homework from before. Correct them with the correct answers. All right, now that you've corrected your answers, let's talk about a couple of things. Particularly, I want to look at the graphs. So from the starter, we have found out that the rational function over here, x squared minus 9 over x plus 3, it simplifies to this function, x minus 3. And that's what this first part of the middle lesson was. These two are actually equivalent because we simplify it. We're allowed to simplify, so they're the same. And therefore, the two graphs should be similar. And when we look at these graphs, which are on the right, they are very similar. They're basically lines, except there's one key difference. If you used your table of values, you will notice that the rational function doesn't actually have a value at x equals -3. Why doesn't it have a value? Well, let's take a look. Let's try subbing in x equals -3. So x equals -3, so then we'll have -3 squared minus 9 over -3 plus 3. So this is 9 minus 9 over -3 plus 3, which is 0 over 0. So this doesn't work. 0 can never be your denominator. Remember, you can't divide something into 0 pieces. So there's no value at x equals -3 for the rational function, yet the linear function, x minus 3, well, it's a line. There's going to be a value everywhere. So how can we indicate this on the graph? Right now I have just this blank space, but we don't really just have blank spaces. We don't just decide like, oh, I'm going to stop dropping my graph here and then I'm going to continue it over there. So what we do is we actually fill in this blank space with a hole. And that is what this lesson is about. So hopefully you got that for the starter. But we're determining how a rational function has a hole. All right, so let's look down at the other page you had. Ask you to use your calculator to copy down these tables of values, and as you can see, they're exactly the same, except that x equals -3. F of x has no value there, but g of x does. Now we've learned that f of x has a hole at x equals -3. But we also determined that f of x and g of x are basically the same function, right? One simplified to become the other. We had x squared minus 9 over x plus 3. This is x plus 3 times x minus 3. And then we had simplifying to become x minus 3. So, I mean, the equal signs show that these things are all the same. They're all equal, except the graphs were not the same. So, f of x had a hole, g of x didn't. Let's look at the equation of f of x. What does it have that g of x does not? More specifically, what did we do to f of x to change it into g of x, even though they're essentially the same equation? And what we did is we factored and then simplified, and this will be the key to finding holes. So how do we determine where a hole is using the equation? We're going to factor, then simplify. Now remember, f of x had the hole and g of x didn't. So what factor does f of x have that g of x does not? Well, it's got to be the factor that we crossed out. That's the x plus 3 factor. That's what's different about f of x. So what else we have to do after we simplify? We take the simplified factor or take any factor that we simplified out. And we'll use that to find the whole. All right, so that factor, that's x plus 3. Oops. X plus 3. That's our simplified factor. So this is from our example. Now, where was the whole? Let's see. The place where we had no value, that was x equals negative 3. So x plus 3 is going to eventually give us a whole at x equals negative 3. So how do we do that? Well, let's see. X plus 3, we got to get it to somehow create x equals negative 3. Well, notice how on the right here we have an equal sign, but we don't have an equal sign on the left, so we're going to need one. So let's add an equal sign. What could this equal to create x equals negative 3? Well, if x equals negative 3, let's see, then we'll have negative 3 plus 3. What does that equal? That equals 0. So what we have to do is we need x plus 3 to equal 0, and that was the factor that we simplified. So let's actually sum that up over here. In general, how do we determine where a rational function has a whole? Let's put that all together. So again, first step, factor, then simplify. That looks terrible. Let's just write that over. Factor, then simplify. Take any factors that were simplified so that were simplified out, and what we did was we set it equal to 0. Oops. And set equal to 0. What this does is this gives us the x coordinate of our whole. X coordinate, our whole. All right, so x coordinate, great. The next question asks us, how do we determine the coordinates of our whole? Well, we have an x coordinate, but what other coordinate? Like, coordinates is a plural word. What other coordinate could they be talking about? Well, if there's an x coordinate, there should also be a y coordinate. So, how are we going to figure out the y coordinate of our whole if we know the x coordinate? If we try to sub it in, remember up here, tried subbing in an x value and we got 0 over 0, which is undefined. So that doesn't give us a y coordinate. So let's see. These two graphs were really similar. In fact, the only thing that was different was the whole. Where the whole is up here, there's actually a point down here. So what we can actually do is we'll use the second graph to help us because there's actually a point there. Now this graph, this was x minus 3. How did this relate to our original function? This was a simplified version. So what we're going to do is we're going to take the simplified function to find the y coordinate. So determine the coordinates of the whole. Take the x coordinate and sub it into the simplified version. simplified function to get the y coordinate. We're going to practice this with an example. All right, here we have another function, h of x. We need to find the vertical asymptote and determine if there is a hole. If there is a hole, we need to find the coordinates. So, vertical asymptote, that's an old lesson. That's last week's lesson. So if you look back at your notes from vertical asymptotes, we still actually start off the same way. We have to factor and simplify. So let's do that. Let's see, we have x plus 2, which will not factor into anything. And then x squared minus 2x minus 8. So we've got to multiply to negative 8 and add to negative 2. So that's going to be x, that's going to be negative 4 and positive 2. That multiplies to negative 8 and adds to negative 2. All right, next step, simplify. These x plus 2's will simplify nicely. So according to the last lesson, to find a vertical asymptote, we take any leftover factors in the denominator and set it equal to 0. So our leftover factor is x minus 4. We're going to set that equal to 0 and solve for x. X is going to equal to 4. There is our vertical asymptote. We just learned how to do holes though, so let's see. Let's get that process up on the same screen. Stop that. Okay, so there's the process up above. Factored and simplified. We have done that. Take any factors that were simplified and set equal to 0. Okay, so for a hole, the simplified factor was x plus 2. Set this equal to 0. That's going to give us x equals negative 2. This gives us the x coordinate. Sub into the simplified function to get the y coordinate. Well, the simplified function is 1 over x minus 4. So the y coordinate, we're going to sub in 1 over x is negative 2 minus 4. So y equals 1 over negative 6. There are our coordinates of our hole. Let's do one more example. So these first workshop problems are about continuity. So that's a bit of a review. Let's look at the next problems. Find a domain, vertical asymptote, and horizontal asymptote for each of these. All right, so to find the domain, we take the denominator and we set it not equal to 0. So we'll have 3x squared minus 15x plus 18 does not equal 0. We have to factor this. That's 3x squared minus 15x, 3x squared minus 5x plus 6 does not equal 0. Can be factored some more. We'll have x minus 2 and x minus 3. And we solve for x. So in this case, x minus 2 does not equal 0, so x does not equal 2, and x does not equal 3. And there's our domain, x such that x does not equal 2 or 3. Horizontal asymptote. From the previous lesson, we learned a horizontal asymptote. We take the leading terms in our numerator and our denominator. That's going to be x squared and 3x squared. We simplify. In this case, our x squared simplify nicely, and we get 1 over 3. And if, according to our horizontal asymptote rules, if we're left with a number, y is equal to that number for our horizontal asymptote. Okay. Vertical asymptote and hole, they start off the same way. We have to factor and simplify. So our numerator factors to this, and we already factored our denominator. For our vertical asymptote, we have to see what's left over, and that's x minus 3. So we'll do x minus 3 equals 0, and x equals 3 is our vertical asymptote.